Okay, so now we're going to take a look at another characteristic of solutions that's known as their colligative properties or colligative characteristics. And when we talk about colligative properties or characteristics, these are characteristics or properties that depend only on the number of the solute particles in a solution. They don't depend on what those solute particles are. So they could be molecules. They could be atoms, they could be ions. It's irrelevant to colligative properties, but all that matters is the number of solid particles or the amount. So this is what is going to dictate these properties known as colligative properties. And there are four of these that we're going to discuss. The first one is the lowering of the vapor pressure. The second is the raising or the elevation of the boiling point. The third is the lowering of the freezing point or freezing point depression. And then the last one is something known as osmotic pressure. So we'll take a look at the vapor pressure lowering first. So remember, when you have a container, let's say, and there is a liquid in it, like this. The container is sealed. Some of these liquid particles at the surface, okay, they can break free and go into the vapor phase. And when they do so, they will exert a pressure when they bounce into the walls of the container. So that is known as the vapor pressure. And this is just going to be of the pure liquid in this case. So what happens is if you have a solution now, which means that in addition to the liquid or the solvent, there might be some other particles in here, like the solute particles. Okay, that has an influence on the vapor pressure now. So the orange things here, these are solute particles. And what happens is that the partial pressure of that solvent or that liquid then over the solution now, so now we have a solution in here, is lowered as a result of those solute particles being present, right? So if you can imagine, if you look at this solvent particle right here, for example, it is actually being prevented from going to the surface by that solute particle that happens to be right above it. So as a result, what we actually see is that the vapor pressure is lowered. Vapor pressure is lower in a solution compared to the pure solvent. And it just has to do with how many of those solute particles are there. The more solute particles you have, obviously, then that prevents more of the solvent from going to the surface and vaporizing, which would make with fewer of those solvent particles in the vapor phase, which would make the vapor pressure a lot lower. So that relationship can be summarized in another law known as Raoult's law, and that says that the partial pressure of a solvent over a solution now is simply given by the vapor pressure of the pure solvent, which is this thing here. So P subscript 1 with the degree sign, that's the vapor pressure of the pure solvent times the mole fraction of the solvent. And we've seen this notation before in that solution. All right, and then the partial pressure of the solvent then in that situation would be in blue. And that's the thing on the left side. Okay, so there's an equation that we can use to calculate what the vapor pressure of a solvent in a solution is if we know what the mole fraction of the solvent is, and if we know what the vapor pressure of the pure solvent is at a particular temperature. Now, what we can also do is if we have a solution that is only made up of two components, one solute and one solvent, we can actually come up with another equation that allows us to determine the change in the vapor pressure. So let's say, for instance, let's rewrite that equation. So the partial pressure of the solvent in a solution is the mole fraction of that times the pressure of the solvent, the pure solvent. So in a solution with only one solute, okay, so remember now the one as a subscript here is for the solvent. Okay, so the mole fraction of the solute then, if there are only two components in the solution, one solvent and one solute, would be equal to the total thing, which is 1 minus the mole fraction of the solvent, right? Just by a simple arithmetic, whatever is not the solvent will be the solute, and the whole thing is just 1 because this is a fraction. So this then we can call this the mole fraction of the solute X or subscript 2. So uh, what we can do then, all right, is we can substitute, can rearrange this equation here. We can say now the mole fraction of the solvent is equal to 1 minus the mole fraction of the solute. We can take this and we can now substitute this into our equation up here. So we end up with now the partial pressure of the solvent in the solution is equal to 1 minus the mole fraction of the solute times the vapor pressure of the pure solvent. Or we can rearrange this. And we can then say the pressure of uh, the solvent in the solution would be equal to, if I just distribute these terms here, right, would be equal to the pressure of the pure solvent minus the product of the mole fraction of the solute times the pressure of the vapor pressure of the pure solvent. And then we can rearrange this even further, and we can say then that P, if I move our stuff around, let's maybe move this term here on this side, and then we move this term on the other side. So what we end up with is the product of the mole fraction of the solute times the vapor pressure of the pure solvent being equal to the vapor pressure of the pure solvent minus the vapor pressure of the solvent in the solution. And this, right, the difference now in the vapor pressure of the pure solvent and the vapor pressure of the solution, that is the change in, or delta, the vapor pressure. Right, so we've just done a little bit of math, a little bit of a rearrangement, a little bit of mental gymnastics, and we're then able to determine or calculate to solve for the change in the vapor pressure when we have a pure solvent compared to the solvent in a solution. As long as you know the mole fraction of the solute, and as long as we know the vapor pressure of the pure solvent, which that can be looked up in different sorts of tables. So what this equation means then is that the change in vapor pressure or the decrease in vapor pressure, so this thing, so the decrease in the vapor pressure is actually now directly proportional to to that thing, which is the mole fraction um, of the solute. And you can think of that as being similar to the concentration, right? The higher the mole fraction, the higher the concentration is going to be. So what this then suggests is that as the mole fraction or as the concentration of the solute increases, okay, the vapor pressure then of the solute, I'm sorry, of the solvent will decrease, right? So the more, and then we qualitatively explain that up here, the more solute particles you have, the fewer solvent particles go into the vapor phase, so the less pressure they will exert. Now we are actually mathematically rationalizing or explaining why that is the case. Okay, we could also look at what's occurring in terms of the entropy of our system. So if you have a pure liquid going into the gas phase, right? So this is then, increase in entropy obviously is going to happen compared to a solution where you have the liquid plus the solid particles. We see, yes, there's an increase in entropy, but the difference in entropy here is a little bit smaller. And what this means then is that there's a tendency then for fewer solvent particles to vaporize. So there's a tendency for fewer solvent particles to vaporize. In this case, compared to the pure liquid case, where there's a much bigger, right, difference in entropy here, this process will be favored compared to the one where there's a solution, where there's a smaller change in entropy. That one's not going to be favored. So the example that we just talked about was when we had a solute. So all of this that we just talked about here was example where the solute was, or solute is non-volatile, meaning it doesn't vaporize. It doesn't go into the gas phase. But what about if the solute is volatile? Well, then what happens if that's the case? Well, if both components of a solution are both volatile, right? So both, and so we're thinking about now both the solvent and the solute can vaporize, they're both volatile. Well, then the vapor pressure of the solution as a whole is just simply the sum of the individual partial pressures, right? And that is something we talked about before in the gases chapter, for example. Now we're looking at it in these solutions where both components are actually volatile. So the pressure, the partial pressure of component A, whatever A is in a solution, is simply the mole fraction of A times the vapor pressure for that pure substance, PA0. And then if the vapor pressure for B is going to be the mole fraction of B times the vapor pressure for the pure substance B, well, then the total vapor pressure would just be the sum of these two things, right? So the mole fraction of A times the partial pressure of pure A time or plus the mole fraction of B times the partial pressure of pure B. We can actually plot that on a graph. So for example, here we have two substances, benzene and toluene. They're both volatile. That's their structures. If we start off with we're going to start here in the lower left portion of our graph. So here, all we have is just, this is the mole fraction of benzene. So in our mixture, we have no benzene. This is just pure toluene that we have. So the partial pressure of toluene there is the greatest. And then the total pressure, right, is just the sum of the partial pressure of toluene, which we're going to do that in orange. And then the partial pressure of the benzene, well, at the beginning, right, there is no benzene, so there's zero partial pressure. And then what we find then is as we increase the amount of the mole fraction of benzene, increasing this way, we see that the partial pressure of the benzene starts to increase. And as the mole fraction of benzene increases, the mole fraction of toluene has to decrease, right? Because they need to add up to one. However, when we add together their mole fractions, we end up with a total. So when we add together their partial pressures, we end up with the total pressure of the solution, and that is just the sum of then each of these partial pressures. So for example, right about here, right, we have a partial pressure of toluene of maybe just over 200, and then same thing for the benzene, the partial pressure there is just over 200. So the sum then, which is going to be right about here, is just over 400. That makes sense. All right, and at the end where uh, we have a mole fraction of 1, so that means the entire thing is now just benzene. Well, then the total pressure is just due to the pressure of benzene, and that's where these two lines, the blue line and the green line, actually are the same. So this is an instance where we have a solution whereby both components, the solute and the solvent, they are both volatile. They both can vaporize very easily. So when we talked about the lowering of the vapor pressure, ideal solutions are solutions whereby the Raoult's law is actually obeyed. So let's take a look at an example of when we can use some of these equations to solve a problem. So it says calculate the vapor pressure of water over a solution made by dissolving 225 grams of glucose in 575 grams of water at a temperature of 35 degrees Celsius. And then we're given that at 35 degrees, the pressure, the vapor pressure of water, just the water itself, is 42.2 millimeters of mercury, right? So if we want to calculate the pressure of water, the vapor pressure of water, we can use our equation. So this will be equal to the mole fraction of water times the pressure of just pure water itself, right, at that particular temperature. So this is given to us as 42.2 millimeters of mercury. We need to find the mole fraction of water in order to use this equation. Okay, so in order to get the mole fraction, we would need the moles of each component. Okay, so we need the moles of the water. So we're given 575 grams of H2O. I want to convert that to moles. So for every 1 mole, we use the molar mass, 18.02 grams of H2O. So that's going to give us 31.9 moles of H2O. We also need the moles of the solute in this case, which is our glucose. Okay, so we're given 225 grams of glucose. We use the molar mass of glucose. We should have been given um, the formula, but we actually talked about glucose before. So glucose has a molar mass of 180.2 grams. So that goes away. So we end up with 1.25 moles of glucose. So then the mole fraction of the water would be the moles of the water, so 31.9 moles of water divided by the total moles of everything. So 31.9 plus 1.25. Okay, and that's going to give a mole fraction of 0.962. So we take this, we're going to substitute that into our equation then for the mole fraction. So we multiply, bring that down here actually, the mole fraction of water times the pressure vapor pressure of pure water at that temperature. So we end up with 40.6. Now, obviously, that makes sense, right? The vapor pressure is lowered. So the vapor pressure is lower for the solution compared to the pure solvent, right? And that makes sense as we've explained previously.